Hello and welcome to Mr. Alvarez's virtual chemistry classroom. Today we'll be doing our very first honors chemistry lesson together. Our aim for today is, how can we calculate the mass of a solid formed and the concentration of the resulting solution after a precipitation reaction? Before we get started, let's do a warm-up question. Question number 1 states, a 250 milliliter sample of 0.750 molar sodium chloride, NaCl aqueous, solution is mixed with a 450 milliliter sample of a 0.650 molar potassium chromate, K2CrO4 aqueous solution. Calculate the resulting concentration of each ion in solution. So first, let's draw a little diagram. We have 2 beakers. The first beaker is 250 milliliters, so 0.250 liters, of 0.750 molar sodium chloride. So let's put that on the bottom, 0.750 molar NaClAQ. When we dissolve sodium chloride in solution, it breaks up into Na plus and Cl minus. For the other beaker, we have a 450 milliliter sample, so it's 0.450 liters, of potassium chromate of a 0.650 molar K2CrO4 aqueous solution. And when this breaks up into ions, it breaks up into 2 Ks pluses and 1 CrO4 2 minus. Chromate's a polyatomic ion you could find on table E. Now I'm adding these 2 solutions together. So that's going to give us a beaker, a bigger beaker, that will be 0.700 liters when I add the 2.250 and the 0.450 liters, so I get a resulting solution of 0.700 liters. And inside I'm going to have Na plus, Cl minus, K plus, and CrO4 2 minus, all floating around. Now it is my job to figure out what the concentration of each ion will be in solution. So next, I must find the number of moles of each substance in the solution. To do that, I need my molarity formula. Molarity equals moles over liters. Let's start off with sodium, Na. I have the molarity, 0.750 molar, and I have the number of liters. So I have molarity and I have liters. So in order to find moles, I must multiply those 2 numbers together. When I multiply 0.750 times 0.250, I get 0.1875 moles. What I've done is I've taken these 2 solutions and added them together, so now the sodium is in a larger volume. It has been diluted. So now I'm going to divide it by 0.700 liters and round to 3 significant figures. I have 0.268 molarity for the concentration of sodium. Once again, the 0.268 is lower than the original 0.750 molar because it's been diluted. The sodium chloride solution has been placed into a larger volume of liquid. Similarly, we should have Cl minus. So we do the same thing. We do 0.750 molar times 0.250 liters, and once again, we are going to get 0.1875 moles, divided by the same 0.700 liters. Obviously, we are going to get the same answer as 0.268 molar for chlorine as we did with sodium. For potassium, it's a little bit different. When potassium chromate dissolves in water and dissociates, you get 2 moles of potassium for every 1 mole of potassium chromate dissolved. So in the resulting solution, we have 2 potassiums. So when we do our formula where we multiply 0.650 times 0.450, we have to double this answer because we have double the amount of potassiums. So when we do that, 0.650 times 0.450 times 2, we get 0 for potassium, 0.0585 moles. We do the same thing. We divide by 0.70 liters. Rounding to 3 significant figures again, we get 0.836 molar. Now notice the molarity of potassium is higher than the original molarity of the solution. It went up. That is because when you dissociate K2CrO4, it dissociates into 2 potassiums, which is going to double your answer. When we do chromate CrO4 2-, we don't double it because there's only 1 chromate in solution. So we do the 0.450 times 0.650, and we get 0.2925 moles. Once again, divide that by 0.700 liters. Round to 3 significant figures, you get 0.418 molar. And as you can see, the molarity of the chromate did go down when we diluted the solution. When solving these monstrous equations, I recommend following these steps. We'll take them slow. Step 1, you're going to write a balanced chemical equation. Remember, we're going to be dealing with ionic compounds, so you're probably going to have to perform the crisscross drop and swap method. Step 2, use table F to identify the precipitate formed. That's going to come out of solution. It's going to settle at the bottom of the beaker. 3, calculate the number of moles of reactants. Draw a diagram modeling the 2 reactant beakers. Draw a diagram. Any visual is going to help you out. Step 4, determine which reactant is limiting. Be sure to account for subscripts. We're not going to have equal amounts here. There's going to be a precipitate formed, but there's going to be a limiting reagent, and there's going to be an excess reagent. Something that slows down, stops the reaction because it's limiting, and the excess, something that's left over. Calculate the number of moles of products produced. Draw a new diagram with a 3rd beaker, with 1 product beaker. Remember to add the volumes of the solution together, just as we did before. Subtract the moles of the limiting reagent from the moles of the other precipitating ion, and convert to grams or molarity as required, whatever the equation asks you to do, the problem asks you to do. Calculate the mass of the precipitate using its GFM, and calculate the molarity of each ion using the new solution volume. I know it's a lot of steps. We'll take the first one together slow. So for problem number 1, it states a 25.0 milliliter of 1.00 molar NaCl is mixed with 35.0 milliliters of 2.20 molar AgNO3. A precipitate is formed and falls out of solution. Calculate the concentration of all ions remaining in solution after the precipitation stops. Let's take a look at this reaction. Here we have the 25 milliliters of 1.00 molar NaCl, and in the second beaker we have the 35 milliliters of the 2.20 molar AgNO3, silver nitrate. We're going to mix them together. And as you can see, even without stirring, a white precipitate is being formed. Okay, so let's see what happened. Our first beaker, which contained 25 milliliters, which is 0.025 liters, of 1.00 molar NaCl aqueous. That means when the sodium chloride dissolved in water, it dissociated to Na plus and Cl minus. In the second beaker, which was 35 milliliters, which is 0.035 liters, you had a 2.20 molar solution of AgNO3, AQ. When that dissolves in water, that breaks up into Ag plus and NO3 minus. Let's first calculate how many moles of each substance we have in each beaker. For sodium, to find out the number of moles of sodium, you'd have to use the molarity formula. Molarity equals moles over liters. I have molarity, I have liters, so if I multiply those two together, I will get the number of moles. So 0.025 liters times 1 will give us 0.025 moles. Same thing for Cl. If I have 1 molar times 0.025 liters, I have 0.025 moles of Cl as well. When I go to the other side, Ag plus, I have 2.20 times 0.035. I multiply those together. So 2.20 times 0.035 is 0.077 moles. I do the same thing for nitrate. I'll do it again just to check my work. 2.20 times 0.035 is going to once again give me 0.077 moles. Now we have to decide who precipitated out of the reaction. What was that white substance that fell to the bottom of the beaker? Well, when I use table F, I find out that silver chloride is insoluble. So when I make my third beaker, which has a volume of 0.025 plus 0.035, which means the resulting volume is 0.060 liters, at the bottom of the beaker, we saw AgCl solid. And floating around in solution, we saw Na plus, we saw NO3 minus, and we saw one other ion. Notice that there are not equal amounts of Ag plus and Cl minus. There is more Ag plus than Cl minus. Cl minus is the limiting reagent. Cl minus got all used up making the silver chloride. In excess is the Ag plus. So silver ions are floating around in solution. The next thing we have to do is determine how much of each substance is in solution. We'll start with how much silver chloride precipitated out of solution. We know that we had the least amount, so that's 0.025 moles of silver chloride sitting at the bottom of the solution. We want to know how many grams of silver chloride were made. So we need the mole formula, number of moles equals given mass over the gram formula mass, or GFM. First, we need to find the GFM of silver chloride. Silver has a mass of 108 grams per mole. And chlorine, we're going to round this one to the nearest tenth, which means it has a mass of 35.5 grams per mole. When we add these two numbers together, we get the GFM to be 143.5 grams per mole. So we have the number of moles, we have the GFM, we multiply them together. Moles and moles cancel out. I'm left with grams. So when I do 0.025 moles times 143.5, I'm going to round to two significant figures. So my answer is I'm going to have 3.6 grams of silver chloride. Next, let's find the amount of silver left over in solution. Before we do that, we have to find the number of moles of silver left. So our original number is 0.077 moles. We have to subtract 0.025 moles because that's how much was used up when we made the silver chloride. So when we subtract those two numbers, we get 0.052 moles of silver, and we can find the concentration by dividing the number of liters. Remember, molarity equals moles divided by liters. So the moles of silver divided by the liters of the total solution, which is 0.060 liters. When you round to two significant figures, you get 0.87 molar. For sodium, Na+, we had 0.025 moles. We divide by 0.060 liters. Round to two significant figures again, and we have 0.42 molar concentration of sodium ions in the solution. Finally, we take nitrate, NO3-. We had 0.077 moles divided by 0.060 liters. And we get 1.3 molar solution. Notice that all of the concentrations decreased once again because we diluted the solution. And silver decreased even more because we lost some to the solid 3.6 grams of silver chloride, and the chlorine is not in solution at all because it was the limiting reagent. Problem number 2 is a little bit trickier. Problem number 2 says 50.0 milliliters of a 2.0 molar silver nitrate solution is mixed with 75 milliliters of a 1.5 molar copper chloride solution. Calculate the mass of precipitate formed and the concentration of each ion. So the very first thing we do is we draw our two beakers. The first beaker is 50 milliliters, so that's 0.050 liters of 2.0 molar AgNO3. That'll break up into Ag plus and NO3 minus. The second beaker has 75 milliliters, so that's 0.075 liters of 1.5 molar CuCl2. What makes this a little bit trickier is copper chloride is going to dissociate into Cu2 plus, Cl minus, and Cl minus. So we find the number of moles of chlorine, we're going to have to double that number when we get there. Let's do the left beaker first. So we have silver. Remember, we want to find the number of moles. Molarity equals moles over liters. We have molarity, we have liters, so we're going to multiply those two numbers together. So 2.0 times 0.050 is going to give us 0.10 moles of Ag, and similarly we'll have 0.10 moles of NO3 minus. We do the same thing over here. we take the copper, Cu2 plus, we multiply the concentration, the molarity, 1.5 molar, times the number of liters, 0.075 liters. So 1.5 times 0.075 is going to give us 0.1125 moles. We do the same thing for chlorine, but once again, when copper chloride, when CuCl2 dissociates into ions, you get 2 chlorines for every 1 mole of copper chloride. So when we get this 0.1125 moles number, we have to double it to account for the 2 chlorines. So for Cl minus, we have 0.225 moles of Cl minus. The next thing we're going to do is we're going to figure out what our precipitate is using table F. So using table F, I find out that silver chloride is insoluble. So that is our precipitate. So next we want to find out what's in our third beaker. Our third beaker, which has a volume of 0.50 liters plus 0.075 liters, which means it's 0.125 liters volume. And what's in the beaker? Well, there's solid silver chloride sitting at the bottom, which precipitated out. There's copper, 2 plus ions floating in solution. NO3 minus ions in solution. And since silver, there's only 0.10 moles, while there's 0.225 moles of Cl minus, silver's our limiting reagent. There'll be no silver in solution, but there will be Cl minus ions in solution. So our next step is to find out how much silver chloride precipitated out. We have the limiting, which is 0.10 moles of silver chloride. To find the number of grams of silver chloride, we need the GFM. So silver has a mass of 108 grams per mole. Chlorine has a mass of 35.5 grams per mole. And when you add those two together, you get 143.5 grams per mole. Once again, the mole formula, number of moles equals given mass over GFM. So I'm going to multiply the number of moles by the GFM. Moles and moles cancel out. I get my answer to 2 significant figures as 14 grams of AgCl. If I want to find out how much Cl is left in solution, how much Cl minus, I have to first take my original amount of Cl minus, subtract the 0.10 moles that I used up to get 0.125 moles. Then I take the 0.125 moles and divide it by the volume. Remember, the molarity equals moles divided by liters, so I divide by 0.125 liters, and I have 1 molar solution of Cl minus ions. 0.125 moles divided by 0.125 liters is going to give me a molarity of 1. To find how much nitrate is in solution, I take the 0.10 moles and divide that by the 0.125 liters. And I get 0.80 molar. Finally, to find out how much copper 2 plus is in solution, I take the 0.1125 moles divided by the 0.125 liters, and I get 0.90 the molar. Problem number 3 is a little bit more difficult than either of the problems we've done before. Problem number 3 states, calculate the mass of lead 2 chloride formed. So this problem is telling us the precipitate will be lead 2 chloride, formed when 85.00 milliliters of a 0.500 molar lead 2 nitrate solution is added to 0.100 liters of a 0.25 molar calcium chloride solution. So the first thing we're going to do is we're going to draw our beaker. The first beaker has 85 milliliters, which is 0.08500 liters of 0.500 molar lead 2 nitrate solution. So before we go any further, we have to figure out what lead 2 nitrate is. We have to perform the crisscross method. So lead 2 means lead with a 2 plus charge, and nitrate off of table E is NO3 with a negative 1 charge. We cross, we drop, we swap, we get Pb NO3 2 aqueous, which means for every lead 2 plus that dissociates in solution, we have 2 NO3 minuses. Let's perform our mole calculation. We know that molarity equals moles over liters, and we want to find the number of moles of lead and nitrate. So we'll start with lead 2 plus, Pb 2 plus. We know the molarity, we know the liters, so we're going to multiply those two together to find the number of moles. So 0.0850 liters times 0.500 molar gives us 0.0425 moles of Pb2 plus. For nitrate, we do the same thing, but we must double the number at the end, because remember, there's double the amount of nitrates in solution as there are lead 2 pluses. So we do, let's check our work, 0.08500 times 0.500 times 2 gives us 0.0850 moles of NO3 minus, double the amount of Pb2 plus. For our second beaker, we already know that we have 0.100 liters of a 0.250 molar solution of calcium chloride. So same thing. We know that calcium is in group 2, so has a charge of +2. Chlorine in group 17 has a charge of -1. So when we crisscross drop swap, we get CaCl2 aqueous, which means in solution, for every calcium 2 plus we have 2 Cl minuses. We'll keep that in mind when we do our mole calculations. We'll do Ca2 plus first. Ca2 plus is moles is molarity times liters. So we have 0.100 liters times 0.250 molar. So we get 0.0250 moles of Ca2 plus. For Cl minus, we do the same thing, but once again, we double the number of moles because there's 2 Cl minuses for every 1 Ca2 plus. So let's check our work. 0.100 times 0.250 times 2 gives us 0.0500 moles of Cl minus, double the amount of Ca2 plus we have. In the problem, they told us that lead 2 chloride is going to be the precipitate. So when we draw our third beaker, which will have a volume of 0.08500 liters plus 0.100 liters, which gives us 0.1850 liters. We know that our precipitate is going to be lead 2 chloride. But before we go any further, we have to figure out what lead 2 chloride is. Lead 2 has a charge of 2 plus. Chlorine, once again, has a charge of 1 minus. When we crisscross, drop, swap, we get PbCl2. So PbCl2 solid will be sitting at the bottom of the beaker as the precipitate. Now, to figure out who's the excess and the limiting, we have to do a little bit of a calculation first. It took 2 chlorines for every 1 lead to make PbCl2. So we have to cut the number of moles of Cl2 in half. So we do that, we have 0.0250 moles of Cl2. When we figure out who's the limiting, who's the excess, we use the original number for lead, 0.0425 moles, and we use the new number for chlorine, 0.0250 moles. We find that the chlorine is the limiting reagent. So that means in solution, we'll have Pb2 plus, floating in solution. We'll have NO3 minus, floating in solution. And we'll have Ca2 plus, floating in solution, but no Cl minus, as that was our limiting. So if we want to find the mass of lead 2 chloride that we have at the bottom of our beaker, we need the mole formula. So number of moles equals given mass over gram formula mass, or GFM. So we have our limiting, which is 0.0250 moles. We're going to multiply that by the GFM. First, we have to find the GFM. Lead has a mass on the periodic table of 207 grams per mole times 1. Cl has a charge of has a mass of 35.5 grams per mole times 2, which is 71 grams per mole. 207 times 1 is 207 grams per mole. We add those two together, we get 278 grams per mole. So to find the number of grams, the given mass, we multiply the number of moles by the GFM, which is 278 grams per mole. Moles and moles cancel out. So we multiply 0.0250 times 278. We get 6.95 grams of lead 2 chloride. Now let's figure out how much of each of the other substances we have left. For Pb2 plus, we have to do some subtraction as we did before. So we take the 0.0425 moles, we subtract the 0.0250 moles we used up making the PbCl2. So we do that, 0.0425 minus 0.0250. We get 0.0175 moles of Pb2 plus left. Remember, our new solution has a volume of 0.1850 liters. So we use our molarity calculation. Molarity equals moles over liters. We have 0.0175 moles of Pb2 plus left, divided by the solution, which is 0.1850 liters. And we get this repeating decimal. We'll round to 3 significant figures. We get 0.0946 mole. For NO3 minus, it's a little bit easier. We take the number of moles, 0.0850 moles, divided by the 0.1850 liters. And we get 0.459 molar when rounded to significant figures, 3 significant figures. And finally, for calcium 2+, we get 0.0250 moles divided by 0.1850 liters. Round to 3 significant figures, we get 0.135 molar. Once again, you can see that the nitrate and the calcium 2+, their concentration decreased because they have been diluted. Nitrate, not as much, because remember, when we dissociated them into solution, they broke up into 2 nitrate ions. Thank you very much for joining Mr. Alvarez's virtual chemistry lesson. Today we covered solution stoichiometry and finding the mass of precipitates formed in a double replacement reaction. Thank you again. Hope you learned something today. Have a good day.